we present RLMuscle, a framework for muscle-driven character animation via reinforcement learning. From a reference motion and a rest pose musculoskeletal asset, it automatically discovers the activations that physically produce that motion and turns them into volumetric muscle deformation. As shown on the left, the traditional workflow relies on tension lines. The artist manually connects two anchor points on the skeleton, and once that line contracts below a length threshold, the muscle bound to it is activated. The alternative is keyframing each activation curve by hand. Both are labor-intensive and non-physical. Ours instead discovers the activations automatically with reinforcement learning, giving automatic activation and physically consistent motion. The challenges here are twofold: control and physics. On control, the first is a redundant action space. We need feasible signals for 284 muscles to actuate joints with 50 degrees of freedom, so we train a supervised network to solve this inverse problem. The second is staying physiologically faithful to real data, so we inject an EMG prior to steer the network toward measured human EMG. On physics, stability and performance are long-standing challenges in 3D simulation. We accelerate our GPU-based XBBD solver with geometric multigrid. And since muscle fiber is anisotropic, we inject the Hill-type constitutive law we already use as a 1D surrogate in RL into 3D, giving us a new type of constraint. Here is the pipeline. The input is a reference motion and a one-dimensional musculoskeletal asset. Reinforcement learning searches for the activations that reproduce it, giving muscle-driven motion. The upper branch takes the bone motion and retargets it onto the 3D skeleton. The lower branch takes the 1D muscle activation trajectory and maps it onto the corresponding 3D muscles. The two meet in our XBBD solver, which produces the final volumetric animation. The same Hill-type law governs both stages, so the deformation follows the dynamics that produce the motion. Now the reinforcement learning stage in detail. Emitting activations for all 284 muscles directly is sample inefficient, so we decompose control into two networks. The policy network proposes a per-joint PD target offset, which stable PD converts into a desired joint torque over 50 degrees of freedom, about a 6-fold reduction of the action space. The muscle network then solves the inverse problem, mapping that torque to per-muscle activations. This inverse is underdetermined and nonlinear. The Hill dynamics realize the muscle torque, which drives the Mu-Jo-Ko rigid body skeleton and produces the simulated motion. That state is fed back as the next observation, closing the loop. Training is driven by a motion-mimicking reward, the discrepancy between the simulated motion and the reference motion target. The two networks are co-trained against it inside a single PPO loop, rather than learned sequentially. We also add an EMG prior to the muscle network loss, which steers the redundant activation solution toward measured human recruitment. The control stage runs on a lightweight one-dimensional asset, 22 joints, 50 degrees of freedom, and 284 Hill-type muscles. Each motion trains in under 2 hours. Each muscle follows the standard Hill-type model: a tendon spring in series with a muscle belly, and the belly holds two elements in parallel. The active element is the contractile machinery, the actin-myosin cross-bridges. Its force length curve is a bell shape peaking at the optimal fiber length, where filament overlap is greatest, and only this term is scaled by the activation. The passive element is the surrounding connective tissue, negligible up to the optimal length, then growing exponentially as it is stretched. The key point is that this same law is later injected into the three-dimensional solver, so both stages share one constitutive relation. The tracking reward rises steadily and plateaus, confirming that the two co-trained networks converge to a high-quality tracking solution. Our results on 4 reference clips: a walk with ground contact, a balance critical kick, a squat, and a swim driven by a hydrodynamic drag surrogate. Blue intensity shows activation, redder regions are muscle belly, whiter regions tendon. All are driven by a 194 muscle volumetric body at 18 milliseconds per frame on a single RTX 4090. At the core of our solver is a geometric multigrid. Previous hierarchical PBD, or HPBD, only gives a formulation for cloth, not tetrahedral meshes. More importantly, it transfers only the position correction from the coarse level up to the fine level, which is not a complete V-cycle. We instead propose a Galerkin-style geometric multigrid. We first coarsen a mesh of 468,000 tetrahedra down to 31,000, then form a prolongator from barycentric coordinates, so each vertex of the fine mesh is controlled by a coarse cage. We define restriction as the least squares state that best reproduces the fine state within that cage subspace, and this Galerkin-style restrictor satisfies the identity mapping. The muscle is simulated in XBBD with a set of position-based constraints: volume, ARAP, attachment to the skeleton, and stable neo-Hookean. Our contribution is the fiber constraint, which carries the Hill law into 3 dimensions, turning activation into contraction and bulging. We now evaluate the system against production and neural baselines and ablate each component. First, against Epic Games' neural musculoskeletal model by Han and colleagues. Our surface is colored by distance to their reference, and the deviation stays small over most of the torso. The essential difference is provenance. They recover activations from a static purpose solve, hours from forward dynamics. Muscle volume over the same sequence. Hours and Epic behave comparably here. Both stay within roughly 2% of the rest volume, so in both cases the volume changes only slightly. Next, against Houdini's Otis solver, the production standard. Over most of the body we stay within a few millimeters, and we are far faster, 18 milliseconds per frame, against Otis's 20.8 seconds. Are the activations physiologically plausible? We validate against surface EMG from 13 human subjects walking. We steer them by injecting an EMG prior into the muscle network. Each rollout is aligned to the gait cycle, and an EMG loss then minimizes the distance between our simulated activations and the measured human signal, 1 term per synergist group. Without the prior, our activations leave the human band over most of the gait cycle, with correlation near 0. With it, they track the human mean within the band, correlation 0.97, while the locomotion itself is unchanged. Ablating multigrid on a squashed bunny benchmark. With it, the solver reaches tolerance in 53 frames, without it, 621. That is roughly 12 times fewer steps and 8 times faster, despite a small per frame overhead. The same benefit carries to the full body. With multigrid, the muscles hold stable volume under high stiffness. Without it, unresolved low-frequency error produces visible artifacts and far more inverted tetrahedra. On a biceps, we compare 3 fiber constraint formulations side by side: a plain fiber constraint, an anisotropic ARAP constraint, and our Hill-Millard constraint. Each gives its own contraction and bulging behavior at full activation. The plain fiber constraint simply minimizes the fiber length along its direction. The anisotropic ARAP constraint also contracts the fiber length, but stays inversion safe. And ours penalizes the Hill-Millard energy, which shortens the fiber as well, while additionally matching the 1D Hill curve. Here we can clearly see the effect of contracting a single muscle, while the others are held fixed. Finally, collision. With our sign distance field handling, the muscle bellies slide cleanly over bone. Without it, they sink into the skeleton around the knee and lower leg. To summarize, RLMuscle solves the muscle inverse problem by forward dynamics inside a reinforcement learning loop and drives a full-body volumetric muscle model at 18 milliseconds per frame. The activations are validated against real human EMG, and the entire system is released as open source. Thank you for watching.